So good morning, everybody. Might seem like a strange question to start our day with, but who likes pie? Spell likes pie, Jesse likes pie.
Mathematical pie or a slice of pie?
A slice of pie. A nice rhubarb pie, that's my favorite. Mathematical pie is also super, super cool, but talking about pies today. By the way, if it was the mathematical pie, it wouldn't be an E. Just throwing that out there.
Oh, I didn't see that. It's cut off where the screens are.
Oh, okay. So, if a lot of people like pie or pies, why don't we make more pies? Well, I'll tell you my problem with making pies. When I make a pie, it works out only about 70% of the time. The other 30% of the time, I use salt instead of sugar, or bake it for too long, or do something dumb, or just whatever. The pie fates don't line up, and it comes out horrible. So my probability of success when I try to make a pie is 70%. So our probability of success, little p, 0.7. Now, I'm not saying that's bad for pie percentages. I don't know what your pie success percentages are. We're not here to judge me or anybody else, but that's our pie percentage. So, I can put questions over here today. So, if I make or try to make one pie, what is the probability it will work? It'll be good. Well, if we already know, it works out 70% of the time, if we make one pie, it should work out 70% of the time, right? Okay, so 70% or 0.7. Okay, it's a fine question, but it's not terribly interesting. So let's expand this question a bit. What happens if I make two pies? What is the likelihood or probability of? You'll hear that word likelihood fairly often. I have no idea if that's how you spell likelihood. It looks weird to me, but it's a weird word. What is the likelihood? It might even be two words. What is the likelihood one of the pies work out? So that's a little more interesting of a question. Even the idea that one of the pies work out, are we saying that one of the pies work out and the other one doesn't? Or are we saying at least one of the pies work out? because those are different questions, right? Let's stick with one of the pies work and one does not. Fair? Just to give us a really strict question. Okay, so I'm going to go back over here and look at how we would answer this question. So step one, we look at what we're doing. We make 2 pies, and we want to look at what could happen. There are different things that could happen. If we make 2 pies, we could get lucky and we could succeed on both pies, right? We might succeed on one pie and fail on the other. We could fail on the first pie. We could succeed on the second pie. That could happen. Or we could fail on both pies. Those are the 4 possible things that could happen. When we were up here with this first question, if I made 1 pie, there were only 2 things that happened. We could either succeed or we could fail. Succeed happened 0.7, fail happened 0.3. What's the probability of us succeeding? 0.7. It was simple. But now that we have 2 pies, we've got more going on. Now I want you to notice something over here. With the 1 pie, our 2 choices were succeed or fail. But this wasn't a 50-50 chance, right? Often people get stuck with the ideology there are 2 possibilities, success or fail. So there should be a 50-50 chance of the pie working out. But we're better at making pies than that. That logic of, well, how many possibilities work out of how many total possibles requires each outcome to be equally likely. So for example, yes, there are 4 possible outcomes here. 2 of them fit our criteria. So it might be tempting to say, well, that's 2 out of 4. 2 out of 4 is 1/2, so 50% chance. But that doesn't work when each outcome is not equally likely. For example, since we succeed 70% of the time, failing on both pies is pretty unlikely, right? So we can't weight them the same. So what do we do instead? Well, we look at our probabilities. What is the probability of, well, we could even make a tree diagram if we wanted to. We've got our pi 1. That first pi is either going to succeed or it's going to fail. Then the second pi is either going to succeed or it's going to fail. And if the first one failed, then the second one will either succeed or it will fail. So those are our 4 possible outcomes: succeed, succeed, succeed and fail, fail and succeed, or fail and fail. So if we wanted to know the probability of each of these occurring, well, to succeed and then succeed, we succeed at 0.7, we succeed at 0.7. So to end up on this succeed and succeed path, we have to get a 0.7 probability and another 0.7 probability. Remember, ands we multiply, right? 0.7 times 0.7, That's going to be 0.49. So we got about a 50% chance, almost a little bit less, of getting both pies right. It's a good chance of having two pies. What about succeed and then fail? Well, remember we fail at 0.3. So this succeed and then fail is going to be our 0.7 times our 0.3, or 0.21. Okay, so we have about a 21% chance. That's not very high, but a 21% chance of getting the first pie right but failing on the second. Similarly, if to get to this fail succeed, we again fail at 0.3, succeed at 0.7. So 0.3 times 0.7. But that's the same 21%. It's still the same numbers, right? One success and one failure. Do take note of that. That's going to be super important later. This was two successes. This is one success and one failure. This is one success and one failure. It's the same combination. Lastly, we've got a 0.3% chance of failing. So to fail the first time, 0.3. To fail the second time, 0.3. What happens if we multiply those together? 0.09. So we only have a 9% chance of failing both times. That's not bad. We'll get some pi out of this, right? Now, one of the first things for us to check would be, do these follow our rules of probability? Are each of them between 1 and 0? Good, yes they are. Do they all add up to 1? Forty-two plus 9 is 51. 51 plus 49, 100. So they even fit our rules for probability. So we could list the individual probabilities here if we wanted to. We could say this is 0.49, even though we don't need it because it's not part of our question. That's 0.21, that's 0.21. Those are important because that's our one success. And then both failures, again, we're not asked about failing both times, but we know that probability. So if we go back to our question, if we make two pies, what is the likelihood that one of the pies will work and the other does not? Well, that happens in these two different ways, right? So there are two ways to get one success and one failure. So 2 times that 0.21. We could add them up, but I'm pushing us towards a logic here. So that's going to be 2 times 0.21 is 0.42. Seem reasonable? So if we make two pies, what is the likelihood that one and only one pie works out? 42% chance, or a proportion of 0.42. And Michelle, it sounds like you've decided, but that Q is essentially what we're talking about with that 0.3, right? That 0.3 is everything else, 1 minus P. That's our Q, our probability of failure. Now, if we changed this question and said, if we make 2 pi's, what is the likelihood that, let's change this to, what is the likelihood at least 1 pi works out? It's a slightly different question. For 1 pi working out, we would need to take our 2 pi's working out. 2 pi's could, our 1 pi working out, or it could work if both pi's work, right? So at least 1 pi working out is 2 pi's work out, or 1 pi works out, and the other doesn't. I'm stressing that word or, obviously. What do we do when we or? We add. So that's the ways that 1 pi could work out and 1 couldn't. There is one way to succeed at both, by succeeding and then succeeding again. Do notice I'm squaring that. So that 0.7 twice for 2 successes. How many times are we going to fail when we get 2 successes here? How many times? How many 0.3s happen in this scenario?
0.
0. What is 0.3 to the 0 power?
1.
It's 1. Anything to the 0 power is 1, right? So that 0.3 to the 0 power isn't doing anything, really, but it is taking a place. There is one way for this to happen, both successes. It has a success twice and a failure 0 times. Does it seem like we're building up a formula here? Hopefully it does, because that's what we're doing. So that 0.49 plus the 0.42 would give us, boy, a big 91%. Notice this purple formula was still 2 ways that it could happen, because it could happen 2 different ways, of having 0.7 once and 0.3 once. Seeing a little bit of a pattern here? Number of successes, probability of success raised to the power of the number of successes. 0.7 twice, 0.3 no times, 0.7 once, 0.3 once. If we wanted to do this probability of failing on both, well, there was 1.3, another 0.3, so 0.3 squared. How many successes are down here? 0. How many endpoints had this pattern? 1. So one way it could happen. 0 successes, 2 failures. Multiply all that out, 0.09. We're making a formula. Questions about that before we make it a bit bigger? 3 pi's is a surprising step up.
Did you say the one where you wrote in the purple, the 2 ways times the 0.7 times the 0.3?
Mhm.
Did you say that that goes with what you were just talking about, or is it just the one on the,
Oh,
the other side with the exponents? Yeah, the green.
When we say at least 1 pi, we've got to take our 2 pi and add our 1 pi, 1 fail. Because the at least 2 is 2 or 1 successful pi.
Okay, that makes sense.
So we took the 2 successful pies plus the 1 successful pi, 0.49
Okay.
plus the 0.42, 0.91. Cool?
Got it. That makes sense. Thank you.
Sure. So I'm going to make myself some space because we're going to need it. Because I really want at least 1 pi. A 91% chance of getting at least 1 pi. I'm not willing to take that risk. That's a 9% chance that I don't get pi, and that is unacceptable. Fail? Well, fair. So if I make 3 pies, what is the probability? Let's stay with 1 pi works and 2 fail. But then we'll expand it to at least 1 pi works. And we could ask any other question. We could ask at least 2 pies work, exactly 2 pies work, exactly 1 pi works, exactly 1 pi fails, all pies succeed, all pies fail. Any combination we want, we could ask. Fair? So we're making 3 pies now. We got to look at all the things that can happen. Well, what could happen making 3 pies? We could get lucky and they all succeed. We could get somewhat lucky. The first 2 work, but the last one fails. Are there any other ways to get 2 successful pies and 1 failed pie?
Success, fail, success.
Success, fail, success. What else?
Fail, success, success.
Absolutely. We could also succeed, fail, and fail. We could also fail, then succeed, then fail. We could also fail, fail, then succeed. We could also fail, then fail, then fail. 1, 2, 3, 4, 5, 6, 7, 8 different possible patterns. I said 3 gets more complicated, right? It mostly gets more complicated because there are more ways that things could happen. But how many of these are 1 pi works and the other 2 fail? Well, this one, that one, and that one, right? Those are the 3 that, or those 3 fit our criteria. So what is the number of ways this could happen?
3.
It's 3. When that meant number, opposed to hashtag or whatever. kids today. The number of ways that we can get one successful pie and two failed pies, there are 3 different ways it could happen. There are 3 different ways we could get what? How many successes? Well, 1 success. And how many failures? Whatever order the successes and failures are occurring in, there's going to be 1 success, so 1.7, and how many 0.3s? The other 2. So 3 times 0.7 times 0.09, which is 3 times, this is getting harder, 0.063, which is 0.189. Check me on that. You guys have calculators. Anybody calculate that and back me up? Andrew, that's right. Okay. So what's the probability that exactly one of those pies work? 18.9%. That's not bad. I got 2 failed pies, but that's what dogs are for, right? Don't feed your dog pies. It's bad for their pancreas. Questions about that? I'm going to kind of blank out this step. That step's just calculating along the way. Like, why 0.9? Well, because that's 0.3 squared. We fairly happy with that?
Okay, so on like the homework, I know that it's just probably wording it different, and it says that you have 11 trials, like you have 11 seeds that are planted, but 2 of them don't grow.
So instead of seeds planted, we're doing pies made.
Right. So I would do the tree thing the same way.
Yes, but you'll find with 11, it becomes a problem.
Yeah.
So let's get there. We're only at 3, right?
Isn't there an easier way than doing it like that? Maybe.
Gosh, you hope so, don't you?
Yeah.
Give me 5 minutes, maybe
Okay.
6, maybe 6.
Okay.
So if we wanted to change to answer this at least 1 pie, we'd have to take the exactly 1 pie. Then we'd have to add in the 2 successful pies, and all 3 pies work if we want to talk about at least 1, right? But the nice thing is the pattern continues. There are 3 ways that this could happen. In those 3 ways it could happen, there are 2 successes. So probability of success times the probability of success, or probability of success squared twice. And there is 1 failure. So we could multiply that out, find the probability that we get 2 successes, 1 failure. How many different ways can we get all successes? Well, that can only happen in 1 way. All successes. And to be technical here, no failures. So take a moment, multiply those out. It's starting to feel hard. 49 times 3. 147 times 3, 30, 42-ish. I don't know. You guys tell me what that is. $34.3. Anybody back that up? Yes, no.
Yeah, that 0.343 is for the first one there.
Oh, it's for this one up on top? Okay. 0.343. Okay. What's the second one?
The second one, I got 0.441.
441. I did in my head. I got something a little bit more than 42, so that seems reasonable. Anybody else find those numbers? I got one no and some furrowed brows. Let's see, 7% of 49. Yeah, I believe that. I believe that. Kim, yes, you got the 44-1. Okay. Yep and yep. Michelle, you getting those numbers?
No, I'm way off. I'm like 12 something. I think I'm entering my exponents wrong in my calculator.
So let's see, you'd have 3 times 0.7 raised to the second power times 0.3. And 1 times 0.7 raised to the third times, if you want to, 0.3 raised to the 0, but you wouldn't have to put that one in.
I must just be entering it weird. I've tried it with parentheses and with multiplication signs, and I'm getting like 12.6.
12.6.
I think I'm just to do exponentials on the calculator. It's second, and then the little button that has the E with the X, right?
No. The
Oh.
e to the x makes e to that power. The number e. Where is it on the TI in my head? I think it's above the multiplication symbol. Those little caret looks like that.
Oh, there it is. Found it.
Yeah.
Okay.
Camilla, Jesse, Isabel, Levi. What about you guys? Jesse, yeah.
I didn't know about the little caret 3 thing.
Jesse got it, just slow typing in wrong numbers.
Flow's okay. Isabel, okay. Yes, good. Okay.
Got it.
Well, and that was one of the reasons I wanted you guys to do it, because I want to see, are you guys happy with typing these in? Because we got some tools we need to work with. Okay, so then if we wanted the at least one, we'd have to take the 0.343, the 0.441, and the 0.189 and add those together. That's the probability that we'll get all the pies right, the probability that we will get 2 right, 1 wrong, plus the probability that we will get 1 right and 2 wrong. Add all those together. 9, 7, 1, 7, 8, 9. We got a 97.3% chance of getting at least 1 pie. That's pretty good. I can accept that. Before we look at how we're going to handle when these numbers get bigger, because Camille, you're absolutely right. When the numbers get bigger, this methodology starts to get, it works, it just starts to get problematic. What if we jumped in here and asked, what is the probability that all pies fail? Try to find that value in the easiest way possible. So you got a couple options. You could come back over here and say there's one way it could happen in 0.70 times and 0.3, the failure probability, 3 times, and calculate that. You could. But we know the possibility of at least one working, right? If we want the probability of all of them failing, that's got to be everything else, right? So 0.027, which is the same thing as 0.3 to the 3rd power. Either way is nice, but since we already found that 0.973, we might as well just use it. Now I want to do 2 things. One, if you're still trying to catch up and make notes for all this, I want to give you a couple minutes because this is a lot we just did. But for those of you who are doing okay, I want to ask you kind of a next level question and let your brain chew on that while others get organized and see if they come up with any questions. So while we're kind of getting situated here, if you're looking for something to think about here, how many possibilities will will there be for 4 pies? Or 5 pies? Or as Camilla's saying, 11 pies. We had 8 possibilities here. We had 4 possibilities for 2 pies. 2 possibilities for 1 pie. How many possibilities are we going to have for 4 pies or 5 pies or 11 pies? So think about that for a minute, or get your kind of notes situated, or try to see if you can figure out a question that would be helpful for you. And I'll give you a couple minutes to kind of get yourself situated with any of that. And then we'll start trying to do things like 4 pies, 5 pies, 11 pies. Heck, we could bake 100 pies. Who makes 100 pies? Pie salesmen or pie salespeople. Pie shop? Patisseries? I have no idea. There are people who make lots of pies. As you said, Camilla, this could be, you know, planting trees, whether the seeds grow or not. This could be we're making got a manufacturing technique that has a 70% success rate, and, you know, 30% of the things we make fail on our production line. That would be bad, but certainly if it's early in a production line, might be true. You know, so these are any success, failure. This, by the way, is how that chart was made for the Mexican-American people on the jury. So the whole yes or no, are they Mexican-American? That would be a success. Are they not? That would be a failure. This is how that chart is made for 12 people. So that would be, you know, 12 pies.
So you're saying I have to make 11 pies to figure out that question?
If you do, I'll take all the successful pies. And again, I prefer rhubarb, but no.
Well, because there's only 9 successful pies out of that problem.
Yep. I'll take 9 pies. But if that sounds daunting, it should. For making one pie, there were 2 possible outcomes, right? For 1 pie. For 2 pies, there were still 2 possible outcomes out of 2 trials. For 2 pies, there were 4 possibilities. 2 possible outcomes over 3 trials. For 3 pies, there were 8 possible choices, 8 endpoints on our tree diagram. Well, for 4 pies, there are going to be 16 possibilities we'd have to list if we tried to do it this way. If we did 5 pies, 2 to the 5th, just doubling each time, really, 32 different combinations. What about your 11 pies? You guys have calculators. What is 2 to the 11th power? How many of these would we have to write out? How many branches would be on our tree diagram if we made it for 11 pies or 11 seeds or 11 people?
2 with a little caret 11,
Yep.
2048. That's what I did. But I don't think that's right.
That's not. 2 caret 11?
Yep, that's what I put in.
$2,000 what?
That's 2048. I don't think.
A lot.
Is that even right?
Well, we could even find it. 2 to the 6th is 64. 2 to the 7th is 128. 2 to the 8th is 256. 2 to the 9th, I'm just doubling this, right? It's 512. 2 to the 10th is 1024. Double that.
It is right.
48. Absolutely. You want to start listing those out?
No, dude.
No, absolutely not. And we say, well, what if you made 100 pies? What's 2 to the 100th power? Billions of trillions of trillions. It's your calculator will go to scientific notation. It's not going to happen. So, okay, theoretically, we could list them all, but we have to have another way to do that. We need a tool to tell us not what the different combinations are. I want to make a tool that tells us how many ways it could occur, because that's all we need, right? So we're going to take a short dive into combinatorics. Yeah, combinatorics. It's counting theory in mathematics. The different ways we count things up. So let's say, I'm going to use 4 as an example. Let's say we've got 4 things, and we're trying to arrange 4 things in these 4 spots. I've got, A, B, C, and D. I've got 4 letters I have to arrange in these 4 spots. How many choices do I have for what goes in that first spot? Jesse, good, 4. There are 4 choices for what goes there. As soon as I make that choice and put one of the letters there, how many choices do I have for the second spot? I got 3 letters left, right? So 3 letters. Okay, as soon as I've chosen that second spot, how many choices do I have for that third spot? Well, how many letters do I have left?
2.
And then for the last spot, I only have 1 letter left, right? So if I get to choose the first spot and the second spot and the third spot and the fourth spot, that product, 4 times 3 times 2 times 1, 24. There are 24 different ways we could arrange this. Fair? That seem reasonable? What if we had 5? 1, 2, 3, 4, 5. And we had 5 objects over here. Well, there would be 5 choices for the first one, 4 choices for the second one, 3, 2, 1. And we'd have 5 times 4 times 3 times 2 times 1, which is 120. So there are 120 different ways to arrange those 5 objects in 5 spots. Now, if we go to 11, it's going to be a lot, right? Let's just even go to 7. 1, 2, 3, 4, 5, 6, 7, and E, F, G. There'd be 7 ways for the first one, 6, 5, 4, 3, 2, 1, right? In counting theory and in lots of mathematics, this pattern happens a lot. Every time we make a choice, our choice goes down by 1, right? So this idea of taking a number and multiplying by every integer smaller than that number, technically every whole number smaller than that number, because they got to stay positive, has a name and a symbol for doing this. That symbol should say, start with this number, start with 7. And the symbol should mean to us, multiply by every whole number smaller until you get to 1. That symbol looks like an exclamation point. And it's read 7 factorial. That is 7 factorial. And it means take 7, multiply by 6, 5, 4, 3, 2, 1, get your answer. So if we wanted to find 7 factorial, we could multiply 7 times 6 times 5 times 4 times 3 times 2 times 1. Which is, a little tedious, but not the end of the world. We could go to our calculators and realize that our calculators have a little factorial button on them. It's under the math probability submenu. Or, as you can imagine, we could even do it in Excel. Oh, come on, Excel. Why is Excel being weird? Why is Excel being weird? Stop being weird, Excel. Okay, fine. Don't go to Excel. Let's just go to Google. 7 factorial. 7 factorial. 5,040. So 5,040 different combinations of arranging those letters in those 7 spots. That seem reasonable so far? Now, that's not all of what we're going to look at, but that's part 1. That factorial tool is a tool for counting up how many things we have. And I believe I don't have a calculator emulator on my computer anymore because the subscription ran out and they wanted $150 for me to re-up it. I'm not going to pay $150. That's silly. But I believe I'm going to get one. I just have to get a new one. But I believe in your math submenu, go over to the probability menu, and there should be an exclamation point. I think it's down on number 7. Is that pattern right for those of you who've done it? Yes, okay, good. So there's the math button is about there on your calculator. And then your probability submenu, you got to arrow over to that probability submenu. And then down, I think it is number 7, is a factorial symbol. Andrew, is that right?
Looks like it's number 4 on mine.
Is it number 4? Okay. I'm probably just misremembering. So this is a nice tool for counting up how many ways we can arrange things. But the issue with what we're doing with these successes and failures is we don't have a bunch of different letters. We only have S's and F's, right? So instead of arranging 7 A through G's, we have to arrange S's and F's. And notice there's different numbers of ways that those end up being the same thing, right? So that, 5,000 different ways that they could be arranged, we have to combine them so that we're looking at how many ways they could be rearranged. Fair? Now, we could have a fairly long theoretical discussion on where it all comes from, but at some point, I'm just going to want to kind of give you that formula. So let's say we had our 7 trials and we wanted 4 successes and 3 failures. Fair? And we wanted that tool for the number of ways this could happen. So the 7 factorial counts up how many different ways that they can all be arranged. But we've got to divide by the number of successes and the number of failures in the ways that they could be arranged to account for all the copies of the same thing. Fair? So number of ways the whole could be arranged, we usually say n factorial over the number of successes that we want. I'm going to say, well, what do I want? I'm going to say x for the number of successes because that's the variable your book will use. The number of successes factorial times the number of failures, which is n minus x factorial. So Camilla, this formula is one of the answers to your question. For 11 trials and 9 successes, how are we going to figure out how many ways that could occur? This tool does that. If I've got 7 trials with 4 successes, that's my how many ways that could happen. You said 9 trials? No, you said 11 trials, right?
With 11 trials, 9 successes, and two failures.
So 11 trials,
Yeah.
9 successes,
Yeah.
which implies 11 minus 9, the 2 failures, right?
Yes. Yes.
That formula will generate how many different ways that could happen without having to draw out the tree diagram with the, 2,000 different possibilities. The fun part, you go back like 100 years in history and you were writing them out. That was all we had. Calculators, man.
So it's the 11 divided by
Well,
the
it's
9
the 11,
number.
the 11 factorial number
Right. Divided by the
by
9 factorial number.
and divided by the 2 factorial.
Oh. At the same time?
Yep.
Divided. Oh. Oh.
Now, while it's tempting to dive into the calculator and ask the calculator to do all that, one thing to keep in mind is that 11 factorial is supposed to be 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2
Right.
times 1, right?
Right.
Divided by 9 factorial, so 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 times 2 factorial, 2 times 1. Now, does multiplying all that out look like a lot of work?
Yeah.
It doesn't. Once you cancel that with that,
Wait.
because you can reduce fractions, right? Same factor top and bottom. And then 2 goes into the 10 5 times, and you get 55. Now, you can ask the calculator too. We'll even have a better tool than that shortly. Because frankly, getting the factorials into your calculator right can be a little bit tough. Yeah. Isabel, you're like, yeah.
Yeah, because I did it, like cancel stuff out and I got like 220. So that was way off.
The big thing is, wait, 220? You did 220 because what you typed into your calculator was 11 factorial divided by 9 factorial times 2 factorial.
I think I put it as like in parentheses 11 minus 9 factorial, which I would probably still get the same thing, but
Well, yeah, the parentheses have to be there.
yeah. And they are, but I still got 220 for some reason, so.
I got 220 also just now.
Do you have the 9 and the 2 in parentheses?
So I got the numbers I got the factorial number for 11 and the factorial number for 9, and then I divided those.
Uh-huh. That would give you 110. And then
I put in parentheses the 2 times 1.
well, then but you're not dividing it. You have to divide it because that 2 is in a division position. For example, if we take 12 divided by 6, what is 12 divided by 6?
2.
2. So that's 12 divided by 3 times 2. What's 12 divided by 3? 4. 4 divided by another 2. So you got to divide by both of them to get that 2. So that would be 11 divided by 9, well, 11 factorial divided by 9 factorial, and then that answer again divided by 2 factorial, which is just 2, to get to 55.
Oh. And that's always it will be that way.
Yes,
Okay.
that's a vision issue. It seems like, well, it should be multiplied because they're multiplied, but they're both being divided, so they have to both be divided.
Got it.
Oh. So this is, oh, my screen went off. Oh, because I hit the off button. There we go.
Huh.
So if we wanted to figure out for this, my 7 pies over here. Ah, come on. My 7 pies over here. Take a minute just to practice. Figure out what 7 factorial divided by 4 factorial times 3 factorial is.
How do you do that in here? You just put 7 in and then you hit the math button.
You can literally, 7 math probability factorial divided by, begin parentheses, 4 math probability factorial times 3 math probability factorial, end parenthesis. Or as before, you could type it into Google. Or Excel, if my Excel was working, which is being weird. Could you get 35? Okay. So if we wanted to know for our pies, this 7 trials, 4 successes, 4 failures, this formula tells us that can happen 35 different ways. 35 different ways to get a success, that's still 70%, 4 times, and a failure, 0.3, 3 times. Number of ways times probability of success for each success, probability of failure for each failure. Kim, yeah, the recording video yesterday didn't work. I don't know why. I did fix the one for last Wednesday. The recording for yesterday, it didn't record for some reason, so which was unfortunate. I thought we had fun yesterday. I always think we had fun, but still. Oh, sorry, that's on your screen.
Finally.
So anybody have a value that they got out of that? Is that a yes, a no, or I don't want to talk about it?
Yeah, I got roughly 0.23.
0.23. I would believe that. Probability of getting exactly 4 successes, 0.23, that doesn't seem unreasonable. Anybody want to back that up? 23% chance of getting 4 good pies and 3 bad pies?
Okay,
Jesse,
so
back that up?
I just got confused again. How he got 0.23. Because I got the top part equals 35. I don't get it. I don't get it.
So that 35,
divided by 2.
that 35 is the number of ways it could happen.
Yeah.
So the number of ways it could happen times the probability of success for every success and the probability of failure every failure.
Oh, shit.
Middle language.
Sorry.
That's okay. Now, in a lot of ways, that response, however language intensive it might be, is not unreasonable. This is a big calculation mess of a tool, right? And you guys know that I like you guys to see how things work and why they work, right? This is what's happening to make this problem work. But you remember standard deviation, right? We spent a while trying to figure out how to calculate it and all the square roots and all the squaring and all of that. But what did we do after that?
Just use the calculator.
We got a tool, right? For the calculator, there's a nice video on the My Open Math on doing these on your calculator. But Excel's got one too. Oops. Equals, because we're asking it to do something. Binom, because it's a binomial distribution. And notice they come up. Binomial dot dist. Binomial distribution. Again, parentheses. Notice, it's a little hard to see. I can zoom in this part, but I can't zoom in that part. The binomial dist has number S. That's our number of successes. How many successes did we have here? We wanted 4, right? So 4 successes. How many trials?
7.
7 trials. What was the probability of success?
0.7.
0.7, because we're pretty good at making pies. That last one, if you can read that, says cumulative. What does the word cumulative mean?
To me, it means to add up.
That's a perfect response. Add up everything. So do we want to go from 4 successes and add up everything below that? So do we want 4 and 3 and 2 and 1 success? Be at least 4 or at most 4? Or do we want just 4? Well, the question we just did was just 4, right? So essentially this last spot is asking, do we want cumulative or not? It's asking us yes or no, true or false on the cumulative. We don't want cumulative here, so I'm going to put an F for false. Or you could put a 0 for no. Either one works. I'm going to go with the 0. If we wanted cumulative, if we wanted the, at most 4 pies, then we'd put a 1, and it would add them all together. Fair? And there's your number. 23, you said? 22.6%? So it's binomial distribution, number of successes. We use X for number of successes. Number of trials, N. Probability of success, P. And cumulative, yes or no. I don't know if that's how you spell that, but that's how I'm going to spell it. So, Camilla, this is either going to be the best part of your day or the worst part of your day. You've been asking, how are we supposed to handle this question with the 11 trials and the 9 successes and that probability, all of that, right? From the problem on the homework on the seeds. Binom.dis. How many successes were you supposed to get in that problem?
You're supposed to get 9.
9 successes. Out of how many trials?
Out of 11 trials.
What was the probability of the seed succeeding? It was 87% or something like that?
Yeah.
0.87.
Mhm.
Were you asked for 9 or less, or just 9?
9.
I think it was just 9. So
Just 9.
0 for just 9. That's your answer.
How come I got a different answer on my calculator?
What'd you get on your calculator? Use the 0.87?
Oh, no,
Okay.
I didn't. That's
That would be
why.
more. Yeah. So all this discussion today is really about what is this doing when we hit enter? It's doing all of this. And I think it's important for us to know that. It's important for us to understand what we're being asked, where these tools come from, why they do what they do. But also, you can see that very quickly, the number of trials, the number of successes we'd have to go through gets untenable very quickly. It becomes a tremendous amount of work. Even these factorials, doing some of these factorials by hand is actually kind of fun. Trust me, it is kind of fun to do. All the canceling that happens is kind of nice. It's surprising how fast they break down. But at some point, particularly when you have to do it for 4 successes, and then do it for 3 successes, and then do it for 2 successes, and then do it for 1 success, it can be way, way too time consuming. Hence, hey, a nice little tool where we can just type the numbers in and hit enter. Is that almost disappointing? Yeah. You can do it by hand for a while. I have no problem with that. Now, what I want to talk about tomorrow, I know I have to let you go in 2 minutes here, but what I want to talk about tomorrow is look at some different ways problems could be worded, different ways these problems can be expressed, different types of things that are essentially the same problem as these that we looked at today, but that might look different, sound different. How do we interpret all the at most, at least, between this range kind of questions? Like, what if we try to make 10 pies? What's the probability that at least 7, but more than 4 will work? What? How are you? It's not hard to do, but it takes some playing with. Fair? So tomorrow I want to work on that part of this stuff. Questions about today? Other than, did we really have to listen through all of that if it was just going to be this cute little tool? I think so, yes. But
You broke my soul a little bit with all of that, only to give me that at the end.
well, at least I didn't save it until tomorrow.
Thank you. Now I can do more homework.
So go play with that homework. Give your soul a rest and maybe a shot of whiskey. And then let me know if anything comes up or if you have any trouble. Okay, I'll see you guys tomorrow.
Bye. Thank you.
Yep.